Okay, today is November 21st, 2011. We're on lesson 5.5. We're going to be dealing with exponential equations. We've put them on the other side there. The last two lessons we have been working with, we dealt with linear models. And you guys need to know your slope formula for linear models. Then the last lesson we dealt with quadratic equations. Yeah. And today we're dealing with exponential equations. So, as a general idea, a rough sketch of a graph for exponential, there are two types of exponential equations that we're dealing with. This is a model of exponential growth. And I'm purposely choosing these colors for you. This is exponential decay. Essentially, these are representing the same type of equation, but we're using two different words to define them. Okay? It's important you guys recognize when looking at these things whether something is growing or whether it's decaying. We're going to get into examples of that. These are rough sketches of what a graph could look like for exponential growth and exponential decay. Now, what we're going to do first is we're going to go into an example. This is our example 1. Move it up a little. Now, instead of going straight to it, what I'm going to do is I want to prove that this is not a linear equation, not a quadratic equation, but rather an exponential equation. Okay? So, what we're going to do in order to figure this out is I'm actually going to go through the first differences first. And we're going to do it very quickly. Then second differences. So if you remember first differences, we're subtracting the values of our y-axis, which will be our a in this case. So we subtract 25 from 35 gives us 10. 25 from 15 gives us 10. And finally, 15 from 5 gives us 10. Since these are all the same, what kind of model do we know this is? Okay, so because our first differences are the same, we know this is linear. Okay? Now, I want to point something out, because yesterday you guys would have gone over quadratic equations, or Thursday, sorry. And in that case, you'd be working with second differences. Second differences is when you take the amounts of the first differences and subtract them. So we get 10 subtract 10 equals 0, and 10 subtract 10 equals 0. In fact, our second differences are the same. Does that mean this is a quadratic equation? No. Okay? We always do them in a specific order. If our first differences are the same, we actually don't need to deal with second differences, because if first differences are the same, your second difference will always be 0. That's another way to tell if it's linear. Second differences would always be 0 if it's linear. Okay? So we know this is not quadratic. And in the question, if I asked you if this was linear, quadratic, or exponential, as soon as you figured out if it was linear, that's it. You wouldn't have to go any farther. But one last thing I want you guys to look at now is the way to tell if something is an exponential equation. Okay? So I'm just going to move over a little more. It's definitely linear. We already figured that out. We just want to prove that it's not exponential. Now, in order to find if something is exponential, we'll be dividing our y terms. Okay? So what that means is I would take 35 divided by 20, or 25 divided by 35, or vice versa. We're going to do it opposite of the book. So we'll do 35 divide 25. Okay? So 35 divided by 25, 1.4. Next, we're going to do 25 divided by 15. Divide 15, 1.6. And finally, 15 divided by 5. Anyone know what it is, top of their head? Pretty sure it's 3. Yeah. So, when we look at our division of all the y terms, are they the same? Are they the same? No. Because they're not the same, we know that this is not exponential. Okay? So, I'm going to quickly go through the next one. We're going to do all three again, because we need to actually determine what type of model this is. When we do our first differences, 51.4 subtract 64. Oh, geez. 51.4 subtract 64. Negative 12.6. 64 subtract 80. It's going to give us 16. And 100. Oh, sorry. 80 subtract 100. If any of you guys notice what I just did there, it's important that whatever you start with, so I decided to go with the top term, subtract the one below it, you have to keep that pattern up. If you start switching back and forth, your answers will become very different. So I kept doing the top, subtract the next one. So 80 subtract 100 gives us negative 20. Is this a linear equation? No, not linear. The first differences are not the same. Let's quickly look at second differences. That would be negative 12.6 subtract negative 16. So negative 12.6 subtract negative 16 gives us 3.4. And negative 16 subtract negative 20 gives us 4. So we have 3.4 and 4. Is this quadratic? No. Not quadratic. There's a possibility that it is none of the above. So let's find out our last one here. If this is easier for you, sure, do it this way. Okay? Now remember, we're dividing the terms in this one. So in the textbook, they decided to do the second term. I'm going to do the first term from the one below. So 51.4 divide 64. Okay, so 51.4 divide 64. Oh, it'll be nicer if we go the other way, but 0.8. I'm just going to round this, okay? 0.8. 64 divided by 80. 0.8. And finally, 80 divided by 100. I can tell you right now that's going to be 0.8. So is this an exponential equation? Yes, we know it's exponential. But here's the tough part. Is this exponential growth or is this exponential decay? How do you know if it's growth? Okay, our terms are positive. Okay, you could think of it that way. What I want you guys to look at is as the x is increasing, Okay? So is our y values. So because our y values are increasing along with that, that means we're going to have growth. And we're going to prove this. I'm going to quickly just graph it. Okay, so we have our scale of our graph. I'm going to quickly plot the point. 0 was at 51.4. We're going to say that's roughly there. 1 is at 64. 2 is at 80. And 3 is at 100, even though I wrote the number 10. This is getting larger and larger, so we know it is growth. Example number 2, we're talking about what to multiply numbers by when we have growth and decay rates. So first off, let's say the school Neil McNeil has a student population growth. Okay, so that means the population in the school is constantly getting larger. If the population year 2010 is 800 and they have a growth rate of 2%, I want to know what I have to multiply the original population by each year to figure out the next year's population. So in other words, how can I represent 2% as a growth rate? Perfect. So what we need to do is we need to turn this 2% into a decimal first of all. So in order to turn a percentage to a decimal, we divide by 100. Okay, so our side calculation, 2 divided by 100, gives us 0.02. Now what's important is this is a growth rate. So that means the original population stays the same. It doesn't actually go anywhere. So to keep the original population, what is a percentage? What if you had 800 kids out of 800? What percent would that be? 100%. So we also need to add the original population, which is 100%. So in other words, in order to get this equation, I need to take the original population, original pop, okay, which is our 800, and I need to multiply by, in brackets, the original population percentage, which is 100%, plus our growth rate, which is 2%. Now I need to change those two numbers into decimals. So our original population is still our 800. What is 100% as a decimal? Ready? We would take 100 and divide it by 100, just like we did 1. So 100 as a decimal is actually just the number 1. We'll quickly do that on the side here, just like we did before. We're taking 100%, turning it into a decimal, it becomes 1. So we have 1 plus 2% as a decimal is 0.02. So our final equation we'll do in red. In order to represent a growth rate, we'll be taking the original population, 800, times 1.02. So next year's population is estimated at 800 times 1.02. 816 students will be at Neil McNeil next year, if this is right. Okay? That sounds logical. I think we do have a growth rate in this school. Now, Canada's population. It is said that for every family in Canada, they're having 1.5 children. I think that's actually high. Okay? So what that means, 1.5, that means they have 1.5 kids on average. So, what's important is we want to relate this. We want to relate this to a decay rate. In other words, that means that we are decaying by 25% our population every year. Okay, as an average. That's our rough estimate, okay? So in order to do that again, we do the same idea. First off, we need to turn 25% into a decimal. So we take the 25, divide by 100. What do we get? 0.25. Our original population is 33 million. I think that's what it is right now. So we take our original population plus growth rate. I should have put those up there. So we take our original population times the original population percentage. Now, if we have a decay rate, are we adding or subtracting? We are subtracting. So we're using DR for decay rate, okay? That's essentially what I did up here. I just didn't write all the words in. So, our original population is 33 million. The original population percentage. What is 33 million of 33 million in a percentage? It's 100%. So we take the 100% again, and we're subtracting by our 25%. Okay? Now I need to change them into decimals, so we have 33 million. We already know that 100% as a decimal is the number 1. What is 25% as a decimal? 0.25. So we end up with 33 million times 1 subtract 0.25 will be 0.75. 0.75. So, without immigration in Canada, our next year's population, as a rough estimate, would be 33 million times 0.75. A lot. 24 million 750,000. That's a very high decay rate. That's not exactly right, but if you have a country population that's decaying that fast, it drops by quite a few people. In fact, by a quarter. The next thing I want you guys to be able to do is I want you to be able to recognize exponential growth and decay when it's written as a formula. So, if we quickly look, I have 3 different formulas, and we've actually dealt with 2 of them in the last 2 days. Today we're dealing with exponential. I want you guys to be able to determine what type of relationship we have by looking at the formula. So, our very first one, does anyone know what type of relationship this is? Linear. This is a linear relationship. How could you tell? It looks like y equals mx plus b. A major way we can tell is the variable, okay, has an exponent of technically 1. And if you notice, that's exactly what this is here. It's in our y equals mx plus b form. There we go. Okay? So that's our linear model. Does anyone know what our second one might be? How do you know it's exponential? The variable in this one is an exponent. So because the variable is an exponent, that means we're dealing with an exponential function. So we have an exponential function. Our x variable is the exponent. That's how we know it's exponential. And finally, what type of equation is this? This is a quadratic equation. How do we know? The variable's exponent is the number 2. So it's larger than a linear model. In other words, it looks like our equation here. Okay? So we have a quadratic equation. Our x is to the power of 2. Okay, the last major thing I need you guys to know how to do is discuss what the variables a and b do to the equation. Okay? So, what we're first going to do is we're going to work with our a's being the same and the b's of our equation. We're going to see how they affect the rate of change and the slopes in the graph. So we're going to graph this. Our first equation was 100 times 2 to the power of x. Okay? When we take a look at this, this is what our growth model looks like. I want you guys to notice that our model is crossing at the number 100. Okay? So we zoom out though. This is what our model looks like. I'm going to add our next equation. 100 times 3 to the power of x. Oh, I guess this one's kind of hard to see. What I want you guys to notice, okay, the new equation we've put in is in black. If you guys now notice, the rate of change, this was 100 times 2x. This one is 100 times 3x. The rate of change has increased. So the larger our b variable becomes, the faster our equation increases, our rate of change. So it becomes steeper and steeper, our exponential model. Okay? Along with that, I'm going to quickly just change, we'll add another equation. This time we're going to do 50 times 3 to the power of x. I want you guys to now notice that where we've crossed the y-axis is very different now. Our new model, which was y equals 50, x to the power of 3, we're crossing the y-axis at the number 50. So our a variable is affecting where we're crossing our y-axis. Okay? So as the a variable changes, that is where we cross. In fact, because our a was 50, we cross, our y-intercept is 50. Our other two had the intercepts of 100, so they don't cross the y-axis till much farther up the graph. And I'm going to change our fourth equation. Okay, the last major equation we're going to add to this is we're still going to keep our a variable as 50. This time our exponential value is going to be less than 1. So we've been dealing with the numbers 2 and 3 before, so we're greater than 1. This one we're going to have 0.2 to the power of x. Zoom out. Should have used a better equation, but our new variable, I want you guys to notice, it's the darkest graph. All of our other ones before were going upwards, so we were dealing with what? Growth. When our b variable is greater than 1, we're dealing with growth. Our new model is heading downwards and across. What are we dealing with? Decay. So when b is between the numbers 0 and 1, we're dealing with a decay model. Okay, so let's go make sense of this. We'll take a look at these graphs after. So I'll pause this. So I know in the graph we just did, you're right, they look like they touch the x-axis, but they actually don't. This is a better representation. They'd actually never touch the x-axis. And for decay, think of it like this. Imagine you walked halfway to a wall, and then you walked halfway again, halfway again, halfway again. You'd actually never make it to the wall. You just continuously walk halfway there. Your halves get smaller and smaller and smaller. You never actually reach the wall if you continuously approach it at half. So this decay model will get closer and closer and closer to the x-axis, but it'll never touch it. It never intercepts it. It does intercept our y, and we already know where. It depends on what our a value is. That's where we're going to intercept our y-axis. And for all of these, we can quickly make our y-intercept. We can quickly check. We know it's 100 in the first one, 100 in the second one, 50 in the third, and 50 in the fourth. Now, our rate of change, B was greater than 2, so we knew it was growth. And our next one, our rate of change was, sorry, not greater than 2, it was greater than 1, and it is the number 2. And this one, B is greater than 1 again, so again we're dealing with growth. But because B is the number 3, the rate of change is even steeper. So imagine we're doing a slope of a line. This one, our B is steeper than when our B is 2. When B is 3, our rate of change goes up even more than when B was 2. This one, again, B is greater than 1. We know it's growth, and B is 3. And in this one, B is less than 1, but greater than 0. That's important. Because it falls in between, we're dealing with a decay factor. So it's actually heading downwards. Our B in this case is 0.2. And we'll go to the next model and kind of point them out for you. This was our decay, which was 50 times 0.2x. We have 3 of them there. These were all growth models. It's really hard to determine which ones, so we're just going to give you 100 and 2x. So this was our growth, and this was our decay. Okay, so homework, page 315, numbers 1 to 7, and number 13.